Hi everyone, Mr. Lee here. In this video, we are going to go over the period of a spring. Alright, so the last time we covered the simple harmonics, we did the period of a pendulum, but now we're going to do the period of a spring. So to start off, I want to remind us of the equation for the period of a pendulum. You'll notice that I now put a subscript p there to designate pendulum. It'll be 2 pi over L over G. Another version of that equation can be the square version, where we just square everything in order to get rid of this square root. And sometimes you'll see this version, especially when you want to graph things and you want to have a linearized version of the form of the equation. Because if we have a square root in there, we won't get anything that is linearized. All right, so this is the period of a pendulum. And the reason why I want to start off with this is because I want to show you the period of a spring equation and how closely it resembles the period of a pendulum. So for the period of a spring, we're going to have a subscript s to designate spring is equal to that the 2 pi, that remains the same. Okay, the 2 pi remains the same. And we still have the square root. And within that square root are the two variables that affect the period of a spring. Now, before I go into it, I want to show you how the period of a spring can be designated in either a lab form or in picture form. So the two versions is we have a spring that is suspended in the air, or is like attached to something like a little platform, and we have a block, a mass that is attached to that spring, and then we can pull on this mass and it'll stretch the spring, and the spring will bounce boing, back and forth, right? That's the sound the spring makes in cartoons, boing, right? So it'll go up and down, up and down, up and down, and it'll oscillate. And then that oscillating motion is what we call simple harmonic motion. So there's the vertical version, and there's also a horizontal version, where if we have a spring, right, and then we have a block attached to that spring, and it's on like a surface, and same thing, you either push or you pull on that spring and you let it go, and it goes boing, and it goes back and forth. And that oscillating motion is what we call the simple harmonic motion. Okay. So here, within these two pictures that I drew, lies the two variables that affect the period of a spring. One of the variables is the attached mass. The attached mass that is attached to the spring. So both scenarios, we had a mass that we attached. So I'm going to put a m there for mass. And then we'll put m here for mass, right? So we have an attached mass. And the other variable is the spring itself. And we represent that with a lowercase k. And that is what we call the spring constant. Okay, I'll write that down in a little bit. But before we move on, I do want to show you the square version. So same exact thing. This version is there mainly so that we can linearize the graphs and the data, and we could just get rid of that square root. Right, so this is the new form of the equation, or the new equation for today. All right. Now, the mass, the m is in kilograms, right? So this is the attached mass, and k is the spring constant. Spring constant, and spring constant, the units are newtons per meters. Now, I do want to get into the relationship the variable has with period one by one, but before I do that, I want to dive a little bit deeper into what causes this motion, this simple harmonic motion, this oscillatory motion. And so I want to focus here on the horizontal version. All right, so I'm going to draw for us the three different parts of the motion. The first part, we'll have the block there. Right, and then we'll have the spring attached, and then the second image is when the spring is compressed. Okay, and I'll designate the middle part with this dotted line, and you should be drawing this as well. And the next one is when the spring is stretched. okay, when it's all the way out there. Okay, so we have this back and forth motion, right? We start off here, we push it to this position, it bounces back and forth, right? It goes back and forth, back and forth, back and forth. Now, the reason why the motion goes back and forth, and this also applies to pendulums, and I'll show you that in a little bit, is what we call this idea called a restorative force, okay? Now, this is a definition you need to know because this terminology comes up a lot. So right here, in this image, this is what we call the object at rest, right? So if there's no motion, this block wants to be at that location, and we have a special word for that. We call it equilibrium. Okay, equilibrium is a place where there is no push or no pull. And that's important because a push or pull for us is a force. And so at equilibrium, your F is 0. Okay, that's a very big main idea. Your F is 0. So when the object is crunching into the spring, so when it goes from 1 to 2, the spring is pushing on this object, on object 2. And so I'll do this in a different color. So what the spring is doing, it's pushing against the block. So the restorative force in this scenario will be to the right because it wants to push it back towards equilibrium. And that's the main idea here. The restorative force wants to push it back towards equilibrium. Right? But as you know, it doesn't just stop at equilibrium because an object in motion, it stays in motion. And so the spring and the block, right, it travels from this location, it goes right, and then we want it to stop here at equilibrium, but because an object in motion, it stays in motion, it keeps on going. The momentum keeps it going forward, and then we end up in position 3. So when we are in position 3, it doesn't want to be there, right? Because like it wants to be at equilibrium. And so the restorative force will be pushing to the left. Now, this is a big main idea because as it's approaching its maximum displacement, the force is going against the motion. So this is back to the kinematics unit. So as it's going from equilibrium to position 3, we have a velocity in the positive direction, but the force is in the negative direction. Okay, and as you know, force and acceleration, okay, the acceleration variable is in force, and so we have a positive velocity with a negative acceleration. So as it's approaching its maximum displacement, it's going to be slowing down. And we covered this in the previous video where I was talking about how there is a maximal kinetic energy and a minimal kinetic energy. The same is true for spring. So as it approaches its maximum position, its kinetic energy goes to 0 because the restorative force is going against it, right? It's going against the current motion because it's like, I don't want you all the way out here, right? I don't want you at these two positions, positions 2 and 3. I want you back at equilibrium. So it's like pushing against it. Okay, and that's what we call the restorative force. And the same is true for a pendulum. So the pendulum, right? We have this pendulum. And let's say we started at position 1, equilibrium will be at position 2, and then we have position 3. So when it's at position 1, it doesn't want to be there. And the restorative force here will be like the force of gravity, and then there's like this, well, of course there's tension, but the force of gravity is going to be pulling this object close and closer to position 2, right? But when it's at position 2, it doesn't want to be there because then the object in motion, it'll stay in motion, it'll swing all the way out. So it'll go from position 1, okay, the force of gravity will pull it down. Okay, and it'll be pulled down, pulled down, pulled down. And there's also like the tension force that's also aiding in this motion, and it wants to go to position 2, but because an object in motion stays in motion, it misses it. It's kind of like when you're at the mall, at the parking lot, and your friend's like, "Oh, there's a location," right? But they were looking in the wrong direction. They drive like right past the open spot in the parking lot, right? And then so you're like, "Oh no!" And then you go all the way back out, right? But the restorative force is like, slow down there, buckaroo, all right, and then it slows it down and it pulls it back to position 2. And so that's why we have this back and forth motion, because the restorative force is constantly trying to get you to equilibrium, but you just kind of always sort of start missing, right? And then we have this back and forth effect. All right, so that's the restorative force with pendulums. That's a restorative force with springs. And the other thing that I want to point out, just like I did with the pendulum stuff, is the graphical nature and where we have the most amount of energy. Okay, so let's remind ourselves with the pendulum idea right here. We said that the maximum kinetic energy was down here at the bottom, and the maximum gravitational potential energy was up here, right, at the peaks. So there we have the maximum energy, and the minimum at those points will be the inverse, right? So the minimum amount of kinetic energy will be at where there's maximum potential. Minimum potential will be where there's maximum kinetic. So the same idea is true for here within these springs. And this is one of those, I'm getting out my galaxy pen, this is one of those starred ideas. You need to know this because there will be questions about this. So the maximum kinetic energy is whenever the spring is not compressed. So here in equilibrium, you have maximum kinetic energy, and that's something you should remember. Whenever you're at equilibrium, you're moving the fastest usually. And at the other compressed parts, this should be U sub S for spring potential. That is where you have minimal kinetic energy. In fact, where you have maximum potential, you have zero kinetic. It's not moving, it comes to a complete stop. But as the spring is being compressed, more and more spring potential energy is compressing into it, and you're storing the energy. Now, just as a reminder, let's write down the equation for spring potential energy. It's 1/2 kx squared, and kinetic energy, of course, is 1/2 mv squared. Okay, and gravitational potential, we have mgh. Now, these are equations you should have either memorized or tattooed at this moment. All right, cool. The graph will look the same, right? So if we have a velocity time graph or a position time graph, where here this is equilibrium, right? And if we stretch it out all the way to position x, it's going to have this beautiful sinusoidal curve. Okay. Now the other thing I want to show you is the energy graph. So here we have, what did I say? This is where your velocity is 0. This right here. This is where your velocity is 0. Okay. And at our peaks, all of our velocity are 0. I believe I started last time. And here, right where it's at the equilibrium, okay, where it crosses the equilibrium, I'm going to write EQU for equilibrium. There you have Vmax. Okay, that's when it's going the fastest. So the other thing that I want to show you is the energy graph. And the energy graph is important because we're talking about energy a lot, right? Not only that, but we can use our energy graphs to also describe the velocity graphs. You know what? Why don't we do the velocity graphs before we do energy graphs? So if this is our position versus time graph, right? I'm going to do this right below it. So let's do a velocity versus time graph. So now we're expanding our idea on kinematics. We said that when it's at its peak, our velocity is 0. So what I'm going to do is I'm going to get my red pen to have specific parts. Okay, and I do encourage you to do something similar. Okay, where there are very important parts of this graph that we want to line up. Right, so right now I'm doing where velocity is max and where your velocity is 0. All right, and I'll just stop after this one. Now this is a skill set that they do require you to do, so try this with me. All right, whenever we are fully stretched out, our velocity is 0, so we're going to start off there. Right, we have a velocity of 0. And here we have a negative slope, so it's going downwards, but it's at the equilibrium, so we have maximum velocity. So I'm just going to say our maximum velocity is down here. All right, and then it goes down, 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 down. It kind of flattens out. This is where velocity is 0, so we're back up here. And right here, we see that this line is going upwards, so we have positive velocity. Positive maximum velocity will be up there, right? And so we get this the sinusoidal curve, like so. Okay, and then the trend follows. I'm trying my best to make it line up. Yeah. Right? And then we will just continue this trend, like so. Cool. And so this is a velocity versus, oops, that should be time. This is a velocity versus time graph that is based off of this position versus time graph. And we could continue this even more for acceleration versus time, but that's for another day. Now, the other graph that I want to show you is, of course, the energy graph. All right, let's do a energy versus time graph. So we have energy here, and we have time going in this direction. And we'll have this be 0, and this will just be maximum, whatever that maximum is. J for joules. Okay, so if we're trying to resemble the two graphs that we made, I'm going to start off with our kinetic energy graph, and then we'll do kinetic energy in red. Okay, kinetic energy in red. So we say that we start off with no kinetic energy because your velocity, your starting velocity is 0, and then we go to a maximum kinetic energy because it speeds up, and then it quickly goes back to 0 as the spring is bouncing back and forth. So just to give you a sense of this, when here we have, let's say this is fully stretched, okay, and this is fully compressed in terms of the spring, right? So we have a fully stretched spring and fully compressed spring. And then it'll be this like curve-like shape. Okay, and then this curve-like shape will just continue back and forth, back and forth. Okay, so there's a lot of sinusoidal stuff. Now the potential energy, so this is the spring potential. Remember, the spring potential energy is greatest when there is no kinetic energy, and also when the spring is fully compressed or fully stretched. And so here we said it's fully stretched, therefore we have our maximum potential, and there is no spring potential when it's moving the fastest, and that's when it's at equilibrium, so that's when the kinetic energy is the greatest. And so we get this inverse effect. Like so. I'm trying my best here. I shouldn't have made it so big. But yeah, actually this is pretty good. Probably my best one yet. Alright, so we get this cool little back and forth motion between the energies. Alright, so back to the very beginning. So we went over the energy, we went over the graphs, we went over like where the kinetic energy was the greatest, when it was the least. Let's go over the why behind this equation, and we'll wrap up the video there. So the why. Why is this equation the way that it is? So we have T sub s is equal to 2 pi square root of m over k. Okay, so we can say that the period and the mass, it is square directly proportional, right? I'm going to write dp for directly proportional. So square directly proportional. Why is that? So you gotta imagine it. If you have a spring and you have a mass attached to it, okay, the heavier the mass that is attached, the more it's going to oscillate back and forth because it's going to stretch it more. Okay, so that's why we have that relationship. The heavier the mass, or the more massive the mass, is going to oscillate more and more because it's going to stretch it more. And this k down here, oops, I should do that on the other side. This k, this spring constant. Okay, so remember, the spring constant tells you how spring-like or how stiff a spring is. So the more stiff a spring becomes, the less likely it wants to move. So I'm going to say it again. The more stiff, or the higher the spring constant, the less likely it wants to move. And so that's why we have this inverse proportional. We have this square inverse proportionality, because the more stiff it is, it's like, I don't want to budge, I don't want to oscillate, because I'm just a stubborn stiff spring. So we get this inverse effect. Okay, so this is why if your spring constant goes up, if it becomes more spring-like, your period will go down, and vice versa. For the mass, if you attach a heavier mass, it's more likely to bounce around. Okay, so that's how the two the stuff relate. Now, on a final note, before we do our wrap up, I want you to know that unlike the pendulum, the stretch of the spring has no effect. Okay, the acceleration due to gravity has no effect. So while you're floating out in space, the spring pendulum, or the spring harmonic motion, you can do those experiments in space, and you can, right? There's video footage of astronauts doing it, but the pendulum one, you can't, because the pendulum just won't fall. Okay, it doesn't matter how much you stretch the spring, because of that restorative force, it'll always just pull it right back in. Okay, all right. So quick review. Important thing is you have at least the equations down. You have all these drawings down. There's a lot of very important information, especially the graphs. As you know, the AP exam, they love graphical questions. And the very last thing that I would want you to definitely have is this relationship here. All right. I'll see you next time. Bye-bye.